All right, next up, we are solving a system of equations that has 3 equations. Okay, so the way that we do this is we need to first eliminate one of the variables. So you can use any combination of the 3 equations in order to do that. We'll be using the addition method to do that. I noticed right away that equation 1 and equation 3 here, x and negative x are opposites. So in the addition method, those two would cancel each other out. So those are the 2 equations I'm going to start with as a means of canceling out or eliminating the x's. So we have the first equation and we have the third equation, 6y minus 3z equals 20. So I'm going to use the addition method, or you may have heard it called elimination in the past, to do this. So x minus x cancels out. We have 1y plus, excuse me, 6y is 7y, z minus 3z, negative 2z equals 22. Okay, so now we have an equation, a new equation that has just 2 variables. So we want to go back over here and use a different combination to also eliminate the x's. So we could use this top one and the second one, or we could use a bottom one and the second one. Either one works. I know that I can multiply this bottom equation by positive 2 in order to cancel out the x's. So that's what I'm going to do. But you could use a different combination. All right, so I'm going to do the first equation, or well, I guess it's technically the second equation, 2x plus 5y plus 2z equals 16. And then I'm going to multiply all the terms in that third equation by 2 as a way to cancel out the x's. It is important when you're doing this that if you eliminated the x's here, the second time around you do it, you also eliminate the x's. So I have plus 12y minus 6z equals 40. All right, so we're doing the addition method again. So the x's cancel out. We have 17y minus 4z equals 56. So now we have this equation and we have this equation that both just have 2 variables. So let's see. I'm going to leave that one here, copy this other one underneath it, and then erase that. Sorry, I don't have a lot of space to work with here. Okay. So now we're just going back to the elimination method or the addition method whenever we have 2 variables. Normally we have x and y. In this case, we have y and z. The process is the same. So the y's don't cancel and the z's don't cancel. But we could easily multiply this negative 2 times another negative 2, because negative 2 times negative 2 is positive 4z, and that will cancel with the negative 4. So I'm going to multiply negative 2, all of these by negative 2. All right, so I'm just going to write that down here. Negative 2 times 7y, negative 14y, that becomes positive 4z. Negative 2 times 22, negative 44. All right, now we do the addition method. So you're kind of ignoring this one, and we're just dealing with these 2 equations. Okay, so the z's cancel. Then you just add the like terms. So we have 3y equals 56 minus 44. What is that, 12? Yep. Then we divide by 3 on both sides. Y equals 4. So that's a lot of work, and all we've figured out so far, x comma y comma z, we're looking for the ordered triple solution, is that the y is 4. All right, so now we can plug that 4 back into any of these equations up here to find the z. Too bad I crossed this one out. What was it? 7y y minus 2z equals 22. Yeah, so now I'm going to plug in the 4 here. 7 times 4, 28, that's a z by the way, minus 2z equals 22. So you subtract 28. So negative 2z equals negative 6. Divide by negative 2, and we get positive 3. So the z term, or the z coordinate, I should say, is 3. Now we know y and z. We can plug it into any of these up here in order to find the x. Erase some of this craziness. All right, this, we can go back to any of these original equations. That top one there, it looks definitely the easiest. X plus y, which is 4, plus z, which is 3, equals 2. So we have x plus 7 equals 2. You subtract 7, x equals negative 5. All right, there's our ordered triple for the solution. Let's see if we're right. We have negative 5, come on, 4, and 3. That is the point in which all 3 of these planes intersect. Yay, we're correct. All right, there you go.